Well, you just heard that it took essentially an army of people to organize this event. People have been looking forward to it for a year. There's tension in the air, there's excitement in the air, and if you're organizing an event like this, what you want to do is you want to start out and then build, get better, get better, get better. So by Friday, people are so excited they can't believe it. But to do that, you have to be very careful in who you choose as your opening speaker. You want to make sure it's the worst possible talk of the entire event, because that's going to lay the foundation for everything else. So it is an honor to be chosen as the opening speaker, where the likelihood of technical malfunctions is maximal, and where the expectations are as low as possible. So I have to apologize a little bit, because I'm going to be talking about type deduction. Type deduction is dull, and I never wanted to talk about type deduction. But when I started working on my most recent book, I said, I'm not going to write about type deduction, and then I said, well, okay, I'm going to have an item on type deduction. And then later I said, I'm going to have 2 items on type deduction. Okay, I'm going to have 3 items on type deduction. Okay, I'm going to have 1 chapter on type deduction, which I didn't really want to do, but I found that I couldn't explain a lot of things without assuming some understanding of type deduction. So I want to talk about basically why you care, because type deduction is not the most fascinating topic in the world, but there are some really important reasons to know about it. Interestingly, I have a confession for you. In C++98, I never understood how type deduction worked. That's true, because it worked so naturally. I wrote a template, it deduced the right types. I called the template, it deduced the right types. Life was easy. I didn't know the rules, because I never had to know the rules. And that was great. Now, it turns out that in C++11, the scope of type deduction is no longer limited just to templates. It's in a lot more places. So if you look at type deduction in C++11, well, you've got auto variables, which is an obvious place. And in fact, that was my primary motivation for trying to learn more about type deduction in the first place. Then you've got these wacky things, universal references. You've got lambda captures, which actually also does type deduction. You've got lambda returns, which also does type deduction. You've got decltype, which is a whole new set of rules for type deduction. So suddenly, type deduction occurs in many more places, and it becomes more important to understand how it works. In C++14, they took the sets of rules for type deduction which exist in C++11, and there are 6 of them that I have been able to identify, and said, let's take those sets of rules and make them even more widely applicable. So now all function return types, for example, can be deduced. We've got lambda init captures, which are not quite the same as other kinds of lambda captures. So we now have 6 different rule sets used in a variety of ways, which means that there's more chances for becoming confused. So the main reason I want to talk about type deduction is that I believe that in C++11 and in C++14, it is increasingly important to understand how the language is deducing types for you, because there's an awful lot of it going on. So from what I can tell, this is the landscape for type deduction in C++. And this is C++98. Normally we say there is 1 set of rules for type deduction in C++98. It's for templates, which I think is a little bit misleading, because there's actually 2 sets of rules. One of the sets of rules is if you have a type that is a pointer or a reference that you're deducing for, and then we have a set of pass-by-value rules. There's really 2 rules. In C++11, they then introduced this notion of universal references, which technically are R-value references, but they're easier to understand as universal references. And there's special type deduction rules for universal references. That's a 3rd set of type deduction rules. This is still inside templates. Then we decided to allow lambda functions to have implicitly deduced return types. And it turns out that the rules that lambdas use to deduce their return types is the same as the by-value rules for templates. So it's not a different set of rules, but it's a different application of an existing set of rules. C++11 also introduced decltype, which has a whole different set of rules we'll talk about briefly. Then C++11 also does lambda captures, which is where you capture variables. It turns out those types are also deduced. Those rules for type deduction are based on the rules for pointers and reference type deduction for templates, but they're not the same. So that line there simply indicates they're sort of derived from, but not in a is a substitutability kind of way. It's just a derivation of that. So C++ 11. And of course, we've got auto. And when you are deducing types for auto objects, they're based on the template type deduction rules, but they're not identical to the template type deduction rules. In C++ 14, we also deduce types for auto parameters that are passed to generic lambdas. They use the same rules as template type deduction. So it's a new application of an existing set of rules. We have auto return type, which also is using the rules for template type deduction. We have one of my favorite phrases, decltype auto, which uses the decltype rules, not the auto rules. Don't be fooled. And then we have lambda init capture. And the lambda init capture rules are different from the C++ 11 lambda capture rules. So that should keep us busy for about 90 minutes, is my guess. And because this is the opening talk, because this is a brand new conference, because there's so much in the way of expectation and excitement, I said to myself, what can I do that'll make this really special? And I came up totally empty. I got nothing. There's just nothing. So then I said, well, all right, maybe I'm not thinking about this the right way. I thought, what can they do for me? And you can do something for me. You can help solve a problem that has been nagging at me for a long time. So there's something about my hair. Because I travel a lot of places, people for some reason take note of my hair. And I get this a lot. You know, you look just like, I get it by email, I get it from people in airports, I get it a lot. You need to help me decide who I look like. So here are the candidates. Every one of these people has been suggested that I look like them at least once, and in many cases, more than once. Candidate number 1, John Bon Jovi. Candidate number 2, Mick Jagger. Number 3, Jeff Beck. Number 4, David Cassidy. I like the head tilt on that one. That's one of my favorites. So I'm thinking pretty rockin', pretty musician, which is kind of sad because I barely know how to turn on the radio. But we are not limiting ourselves to the real world. Number 4. He-Man, thank you very much, the staff at Facebook, for that. Lest you think there's only one cartoon character I can resemble, number 5, Prince Valiant. Thank you to the charming people at Reddit for posting that one. I really appreciate that. For better or for worse, my wife claims I look like Alexander the Great. This is why I married her. And our final candidate, and this is so strange, I was going through you think I'm making this up. Often when people are saying these things, it turns out they're holding my passport and looking at me. A lot of customs officials, really boring jobs if you think about it. So last year when I was going through customs in the Bahamas, this guy looks at my passport and goes, "You look like a perfect combination of John Lennon and Bill Gates." And I thought, you spend way too much time in the sunshine. So what I want you to do is solve the dilemma for me. Who do I look like? So it is live, scottmeyershairpoll.com. So during the course of this presentation, when you get bored, I would encourage you to go to the website and make a vote. And with any luck, at the end of this conversation, we will know who I look like. In the meantime, we'll be talking about type deduction. So I want to talk about template type deduction, but I need to be clear here. My original motivation for this was because I was trying to explain to people how auto works. So when I talk about template type deduction, I'm not going to talk about everything to do with template type deduction. I'm only going to talk about the stuff in type deduction that I think is relevant for understanding how auto works. And what I think most people don't recognize, and I had not really grasped when I started with this, is when you do template type deduction for a function template, you're actually deducing two different types. So if you have a template for some function f, It has a template parameter t, which you clearly have to deduce the type for. That's what people generally focus on. But then there's going to be some declaration, usually, of some parameters. And you're also deducing a type for what the parameter is. And typically, the type of the parameter is not the same as the type that is deduced for the template itself. So you're actually deducing two different things. And it's important to keep that in mind, because that's going to affect some of the other stuff we do. What I have found is that when trying to understand how template type deduction works, it is easiest to break it into three completely different cases, because the rules that are used for deducing t depend on the form of the parameter declaration. It's not just let's deduce t and then worry about the parameter. The way you deduce t actually depends on the parameter. So the two interact in funny ways. So I'm going to deal with three possible cases. The first one, usually people start with, well, how does it work with pass by value? I'm not going to start with pass by value because pass by value is not the simplest case. The simplest case is pass by reference and pass by pointer, where we're dealing with what I will call normal references, which means references that either are L value references or R value references, but are not universal references. So if you're dealing with type deduction for a reference, type deduction is really, really simple. Essentially, if I need to go back one slide here. So what we're always trying to do is we have some call to the function f with some expression. And what we're trying to figure out is what is the type of t and what is the type of the parameter based on the type of this expression. So if somebody passes in an expression, you're trying to figure out two types from that. So the first thing is, if the expression itself is a reference, you're going to ignore that. You're going to pretend like it's not a reference. And after that, you essentially do pattern matching from that point forward. And I'm not going to run through the detailed rules here, but if we have an example here, I've just got this function f. It takes an L value reference. X is an int. Cx is a const int. Rx is a reference to a const int. If I call f with x, well, this is an int, so t becomes int, and param becomes a reference to an int, just as you would expect. If it's a const int, then t will be const int, and param will be a reference to a const int. Rx is a reference. So you throw away the fact that it's a reference, and you treat it as if it were just a regular constant, which means you'd have the same kind of type deduction you would get if it were declared just as a constant. And the only thing that's really interesting there is that even though Rx is a reference, the type t that is deduced for the template is not a reference. So that's all straightforward. If you were to change the type of the parameter so that instead of being a reference to t, it's a reference to a const t. All I've done now is I've changed the type of the parameter. That will change the type that is deduced for t, because the way you deduce t depends on the way the parameter itself is declared. And essentially, in this case, we're just moving the const around a little bit. So same things, x is an int, cx is a constant, rx is a reference to a const int. So now when I call f with x, well, in this case here, t is still int. The parameter time is now a reference to a const int because of this const here. If the argument itself, if cx is already const, then t is no longer going to have this const deduced, and instead it's just deduced as int, and the parameter type is still referenced to const int. Similarly, rx is treated the same as cx for the same reason as before, because we throw away the reference-ness. But notice how the type deduced for t depends on the declaration form of the parameter. If we have pointers, the rules are essentially the same. So in this case here, if we have a pointer parameter, x is 22, pcx is a pointer to a constant version of that. If I pass in the address of x, t is deduced to be int. The parameter type is just a pointer to an int. If I pass in a pointer to a constant, then t will be deduced to be constant, and the parameter type will be pointer to const int. And if I were to run through const pointers, it would behave exactly the way you expect. And right about now, voting in the hair poll should be looking pretty good. There are no surprises here. What was a little bit surprising to me was, even though I find that most people get those rules, things all behave very intuitively, when I tell people that auto uses the same rules as template type deduction, in many cases people get confused. But it is exactly the same set of rules. So if we're declaring a reference type here, so this is auto ref, so in this case here, auto is going to play the role of the type t in that function template. And when I say that, I mean it in a very literal sense. The rules in the standard for how auto works literally say, go and see how template type deduction works. So for purposes of what we're talking about right now, they're exactly the same rules. So in this case here, this is we're going to give us a reference to an int because auto will deduce to be int, just like the template would be if you passed x to that function template. If I say auto ref of cx, because this is a reference to a const int, auto is going to be deduced to be const int, and we get a reference to a const int. Same thing for v3 here. And if I were to run through things in detail here with a const auto ref, this behaves exactly the same as the function template, where the parameter is of type reference to const t. And again, we get it's a matter of where the const is deduced, but it's exactly the same as templates. So should not be any surprises. So at this point, if that was all I had to say, really there would have been no reason to say anything at all. Things just behave exactly the way you expect. There's no surprises. The first difference is when we get to universal references. How many people are familiar with the term universal reference? Okay, it is not an official term in the standard. It's not an official term in books except mine. Universal references look like R-value references. So this looks like an R-value reference, tref. But what it represents depends on what it is initialized with. And in particular, if you initialize this kind of reference with an L value, then this reference becomes an L value reference. So although this looks like it's an R value reference, and that suggests that it will only bind to R values, in fact, it is both an L value reference and an R value reference, and it will bind both to L values and to R values. It is this distinctive behavior which leads me to give it a different name, because it doesn't behave like normal R value references. So same initializers we had before, x, cx, and rx. Now, in this case, it's important to know x, cx, and rx because they're all identifiers. You can take the address of every one of them. That makes all of those L values. And because they are L values, this means that type deduction works in a special way. In particular, when you call this template and you pass an L value, the type that is deduced for t will be an L value reference. This is the only case in template type deduction where a reference type will be deduced for this type parameter here. When you deduce an L value reference for t, you end up with, well, if you just substitute tref, because it's an L value reference, followed by two more references, you get an L value reference to an R value reference, and through the magic of what is known as reference collapsing, it all collapses down into an L value reference. I find it much easier to simply remember that if you call a template that takes a universal reference with an L value, then this parameter type becomes an L value reference to int. So universal references have the unique characteristic that what looks like an R value reference in the source code becomes an L value reference in the instantiated template. And the reason this happens is because when you have a template of this form and you pass in an L value, this parameter type becomes an L value reference because t is actually deduced to be a reference type. Only universal references behave this way. So in this case here, Cx is an L value, which means that t will be deduced to be, there we have. Well, anyway, Cx this will be deduced to be an L value reference to const. Yeah, L value reference to const, and the parameter type will therefore be an L value reference to const. In this case, f of Rx, because this is an L value, t will be an L value reference to const, which means the parameter type will be L value reference to const. The number 22, the integer 22, by definition is an R value. Because it is an R value, the normal type deduction rules kick in. The type of 22 is int. Int will be the type that will be deduced for t, and as a result, this will simply become int ref ref. This will therefore be an R value reference. So as a result, t will be int, and the parameters type will be int ref ref. So that's how things work with universal references. Special rule for deducing the type t in particular becomes an L value reference. This leaves by value parameters. Now, by value parameters, the first thing is whatever expression is passed to the function, if it's a reference, you throw the reference away just like you used to. That has not changed. Then if the expression is const or volatile after you threw away the referenceness, you throw away the const or the volatile. And t is the result of that. So in this case here, we have a pass by value parameter. So we're going to pass in x or cx or rx. It's useful with pass by value to sort of step back and recognize what's going on. We're creating a completely independent variable here. It's a brand new object. So the fact that it's being initialized with a const object makes no difference. The new object isn't necessarily const. The fact that we're initializing it with a reference makes no difference. We're creating a brand new object which is not a reference. So this is just creating a brand new object. So we throw away the referenceness of the initializing expression. We throw away the constness or the volatileness of the initializing expression. And that becomes the type that is deduced for the brand new variable. My experience is this is where people get a little bit confused when it comes to auto. So in this case here, we have the same initializers, 22, and then a couple of variables x. So auto means this is a brand new variable. It's not auto ref, it's not auto star. This is a brand new variable. So x is an int, so v1 is an int. Cx is a const int, but the fact that Cx is const makes no difference to us. v2 is just an int. Rx is a reference to a constant, but the fact that it's a reference to a constant makes no difference to us. We're creating a brand new variable. And as a result, v3 is also an int. The same rules apply for auto. Now, auto is never deduced to be a reference type. Just the word auto by itself never becomes a reference. So if I say auto v4, I'm creating a brand new variable here, in which case Rx is a reference to a constant, but this is still going to be an int because we don't care about what we're initializing it with. We're creating a brand new variable. If you add a reference to auto, either an L value reference or a universal reference, then you use the by reference template type deduction rules, which I talked about before. So in this case, v5 is a reference to Rx, so Rx is a reference to a constant, so v5 is also a reference to a constant. We don't throw away the constness. And auto ref ref, this is a universal reference, auto ref ref. It is being initialized with Rx. Rx is an L value. That means that this whole business here, auto ref ref v6, becomes v6 is actually an L value reference to a constant. Notice that the source code says it looks like it's an R value reference, but this is actually a universal reference. So the deduced type is L value reference to const int. When we are dealing with type deduction, it is important to distinguish between an expression that is const versus an expression that contains const. because they're not the same thing. The most common place you run into this is when you have pointers. And in particular, when you have a pointer, you can have a constant pointer, in which case the expression is const, or you can have a pointer to const, in which case the expression contains const. And you can have a constant pointer to const, which is a constant expression containing const. And what we've said about by-value parameters is if an expression is const, because it's by-value, you ignore the constants, you're creating a completely new copy. So in this case here, I've got this function. I have a parameter which is a constant pointer to a constant int. I have a parameter which is a pointer to a constant int, and a parameter which is just a pointer to an int. In this case here, notice I'm saying auto. Auto creates a brand new object unless it is adorned with pointers or references. But in this case, this auto has no pointer or reference adornments. Param1 is a constant pointer, but we're creating a completely independent pointer. So the fact that we're initializing it with some pointer which happens to be const is irrelevant. The pointer itself that we get is not const. But that pointer contains constness. It points to something which is const. That const is retained. So in this case here, P1 is going to be of type pointer to a constant int. The fact that param1 is const is ignored. The fact that param1 contains const is not ignored. P2 is of type param2. Well, param2 was not const in the first place, so P2 is just a pointer to a constant, and P3 is just a pointer to an int because there was no const involved in the first place. Now, what I told you earlier about by-value parameter passing is if something is const or volatile after stripping it of its referenceness, you ignored the const or the volatile. Normally, what people say is top-level constant volatile is ignored. That's what you'll hear more frequently is top-level constant volatile is ignored. The only problem I have with this summary that top-level constant volatile is ignored is that it only applies if you are dealing with by-value. If you're dealing with passing something by reference or passing something by pointer, then those top-level constant volatiles are not ignored. So they're only ignored if you're making a completely independent value. So this is the same function I had before, same parameter types that I had before. In this case here, P1 is an auto variable. I'm creating a brand new copy. That's that by-value copy. So when I initialize it with param1, which is a constant pointer, the result is a pointer to a constant int. The pointer's not const. But if I throw a reference in here, so now P2 is a reference type. Now we go by the reference type deduction rules. The reference type deduction rules retain that first const. So as long as you understand that when people say top-level constant volatile is ignored, they're only referring to by value, you're in good shape. But if you think that it's always ignored, you need to correct your thinking. That's pretty much what I want to say about template type deduction. Template type deduction covers 3 of the 6 different ways that types are deduced in C++. There's also a couple of special cases. One of them is for arrays. One of them is for functions. Basically, if you're passing an array name or a function name to a parameter that is a reference type, then you actually get a reference and a function. But if you pass it to something by value, they decay into pointers. So sometimes you get pointers and sometimes you don't, depending on exactly how things are being passed, but I don't want to dwell on that. So that's template type deduction. Auto type deduction, from my perspective, was pretty simple until Friday. Something happened on Friday. But I'll get to that in a moment. Auto type deduction is the same as template type deduction unless you have a braced initializer. Now, this is very important. A braced initializer, like curly brace, 1, 2, 3, curly brace. That's a braced initializer. A braced initializer has no type. A braced initializer has no type. A braced initializer has no type. No type corresponds to a braced initializer. Which is why, if you try to call a function template with a braced initializer, type deduction will fail. Of course type deduction will fail. It has no type. And yet, if you initialize something with auto, with a braced initializer, which has no type, a type will be deduced. It'll be an initializer list, assuming that the contents are all the same. So in this case here, if I say auto x1, curly brace 1, 2, 3, close curly brace, the type will be initializer list of int, even though curly brace 1, 2, 3 has no type. It's an initializer list of int because these are all integers inside. If I say auto x2 equals curly brace 1, 2, 3, we get an initializer list of int. Until Friday. I thought, all right, auto's a little weird, but other than that, we're in good shape. That's the rule. And then Friday came. I got some email on Friday. Bringing to my attention N3922, which I actually had known about because I blogged about it in March and then did everything I could to put it out of my head. N3922 said, the rules for auto are too simple. The motivation, not expressly written in 3922, but I can read between the lines, the motivation was Scott's job is too easy. We need to introduce a new form of distinction. So N3922 now says whether there is an equal sign makes a difference. According to N3922, this is not part of C++14. Not part of C++14. This is a proposal. The proposal says that if you don't use an equal sign, in which case we are using direct initialization, there's a new set of rules. So the old set of rules says auto x2 equals 1, 2, 3. You get an initializer list of int. Basically, if you have an equal sign, you get the initializer list of int, just like I told you. So equal sign means you get the same behavior I just described. But if you omit the equal sign, if you decide you want to save a couple of characters, you do not use the equal sign. New set of rules. The new set of rules are, if the braced initializer has exactly one element, the type that auto will deduce is the type of the element inside. So if you say auto x3, curly brace 17, close curly brace, then the type will be int. That's not how it works in C++14. In C++14, it's an initializer list of int. And if you use no equal sign, what's known as direct initialization, with multiple values, then we're going to assume you meant to only have one value, and this is therefore a mistake, and your program should not compile. N3922. Now, what you should be thinking is, they haven't even officially totally ratified C++14 as far as I know. Isn't there still a little bit? Herb? Where's Herb? Herb's sleeping. As far as I know, there's still a little bit of paperwork that has to occur before C++14 has been issued as an official ISO standard, as far as I know. So you might be wondering, why is he telling us about N3922, one of 8 zillion proposals that the Standardization Committee will consider? Well, because the email I got on Friday said, oh, by the way, this is the way Microsoft's compiler has already been implemented. So I didn't want a whole bunch of people using Microsoft's compiler saying, Scott, you liar. Although I need to point out that if I am in fact lying, remember, setting the bar as low as possible for the first talk. Yeah?
Could you just roll back to the previous line? So would that first error be directed with greater than one element? No greater or equal?
Thank you very much. You're right. So my mistake. This is an error if it's greater than one element, not greater than or equal to. Thank you very much. So that greater than or equal to is incorrect, and that greater than or equal to is incorrect. It should be greater than 1. Thank you for the correction, and I apologize for being carried away with a little bit of special symbol exuberance in PowerPoint. I spent seconds looking up that symbol, I'll have you know. So. You have to speak much louder.
Does that mean that there's code that would compile to a different semantic than Microsoft?
Okay, so the question is, does that mean that the code will, basically, does that mean that the meaning of source code can change with this? And the answer, of course, is yes, because under C++14, this would deduce an initializer list of int. Under 3922, which is what Microsoft's implementing, this deduces to be int.
So it's a breaking change.
It's a breaking change. It's an enhancement. So I'll talk more. I'm happy to deal with questions later. We have more material we want to go through. And I want to point out, N3922 is not part of C++14. However, it is my understanding from people who I believe in a position to know that it is highly likely that this change is going to be part of the next C++ standard. I can't resist remarking that I have tried informally for at least 2 years and possibly more like 3. I do not understand why even in C++11 and C++14 there is a special auto rule doing type deduction for braced initializers. I simply do not understand why that exists. I have not been able to find any motivational argument in terms of a standardization document. I have posted a couple of times on my blog asking for people to help me out. I have talked to members of the standardization committee. I simply don't understand why this rule exists. So obviously it does exist for some reason. It didn't write itself. It's in the standard for a reason. I just don't know what it is. So if somebody can find out for me, I really would be deliriously happy to know.
My understanding is why it always isn't reduced to a standard initialized list, because you've got a bunch of objects, literals, inside a code base. Why isn't it always initialized?
Okay, so essentially your question is, essentially your question is, why don't they always deduce it to be an initializer list? Well, the answer to that is really easy. Braced initializers have no type. At any rate, so the only reason I'm pointing out this new behavior with 3922 is simply because for at least one major real compiler on the ground, it has already implemented these new semantics. So you need to be aware that if you're working either with Microsoft's compiler or with multiple compilers, one of which is Microsoft's, that the behavior that I have described as regards type deduction and auto is going to be inconsistent across platforms. So as far as I know, at least with the regular switches, GCC and Clang don't behave that way, and I haven't tried any other compilers. So that's an interesting little twist. So I do think it's sort of interesting that C++14 is not done yet, and already things are changing. So that makes people like me who are authors deliriously happy. Because you really like to be able to write stuff and know that it will be out of date by the time it gets printed. I want to talk now about lambda capture type deduction. So there are 3 kinds of capture in lambdas. First, you can capture by reference. If you capture by reference, you get the template type deduction rules for reference parameters. Nothing new there. In C++14, you can use what's known as a nit capture, what sometimes is called generalized lambda capture. That uses auto type deduction rules, including the ones we just talked about with braced initializers. Uses auto type deduction rules. And then you can capture by value. Now, by value is a really interesting case because it uses the template type deduction rules, except it doesn't throw away const and volatile. It's the only place in C++ where things by value don't throw away const and volatile. So here I've got a scope. I have a local variable cx, which is a const int. I create some lambda, and I say I want to capture cx by value. When you do this, the compiler generates a custom class corresponding to the lambda that you've created. It then creates a data member for the variable that you've captured. The type of the data member is const int, even though it's a completely independent copy. It's the only place in C++ where if you are creating a completely independent copy, you still preserve constness and volatileness. Now, What's interesting is how this differs from a nit capture. So C++ 14 introduced what's known as a nit capture. A nit capture is a mechanism that permits you to say, I want to introduce a brand new data member with a particular name into the capture class, and I want to give it an initializer. So it looks like this. So this says I'm creating a lambda, and when I say cx equals cx, this says create a brand new variable called cx inside the class that you generate, and initialize it with cx, which is this cx. So the left-hand cx is in the scope of the class that's being created. The right-hand cx is in the scope where the lambda occurs. So this says create a variable called cx, which is a copy of cx. The variable that's being copied is a constant. The copy is an int because it uses auto rules. Auto rule says throw away the constness. However, if you just use the regular by value capture syntax, then because this is const, the constness down here is retained. It's an interesting little wrinkle that only exists for by value lambda captures. Now, in fairness, most of the time, you are not going to run into this problem. The reason you're not going to run into this problem, when I say problem, you're not going to be surprised by this behavior, because by default, the function call operator in a class generated from a lambda is const. So if I say, for example, I want to set cx to 10, the compiler is going to generate a function call operator which will be const. By default, it's going to be const. So notice that this is now just a regular int. This isn't const at all. This will copy that int as a non-const int into the class. So it's clearly a modifiable int. But inside a const member function, you can't modify a const inside a const member function. So this line here will fail to compile, and the reason it fails to compile is because the member function itself is const. That has nothing to do with const retention, because notice that the local variable being captured is not const. However, if you declare your lambda mutable, when you declare it mutable, it means the function call operator is not const. So now, if you have a local variable which is const and you capture it by value, it will be copied into the class as a const. And now this won't compile because you have a constant value in your class. Only place in C++ where CV qualifiers, as they say, are retained when you're creating a brand new object. I don't think we have enough gratuitous animal photographs. Now, about this time, you might be thinking, OK, so sometimes it uses these rules, and sometimes it uses those rules. And then we got funny rules for lambdas, and then it depends on exactly how things are captured. And we've got reference rules, and we've got pointer rules. And it's easy to wonder whether the compiler is deducing the types that you want it to deduce. So it would be nice to have some ways to have the compiler tell you what it's deducing. And I want to talk about a couple of different ways of doing that, which I have found to be very useful. So the first one came from Stefan Lawade at Microsoft. And he pointed out what you do is you create a template which is just declared, it's not defined. So TD for me means type displayer. It's a declaration, it's not a definition. And so now, inside my template here, if I want to know, OK, what type was deduced for T and what type was deduced for the parameter, what I'm going to do is I'm going to instantiate the template with the types that I want to know about. Now, the compiler is not going to know how to instantiate the template because I didn't give it a template definition, which means compilation will fail, and it's inside the error message I'm going to be able to get the information that I want. That's the basic plan. So I say, OK, I'm going to create a variable t type of type td of t because I want to know what t is, and I'm going to declare a variable param type of TD of decltype of param, so TD instantiated with whatever type param has. We'll talk about decltype shortly. And in this case, if you do it with our friends x of 22 and rx is x, and we call f of rx, so I call the template. So GCC says, okay, TD of constant t-type and TD of constant ref param type. So it tells us exactly what the types are that we wanted to know. Different compilers have different outputs, so Microsoft's compiler does it a little bit differently. So it'll say, okay, t-type uses TD of t with t equal to constant, which means t is constant. If you want to know what param type is, notice that it's TD of t ref with t as const int, which means that the parameter type is reference to const int. You have to kind of put the two pieces together yourself. And Clang is similar to GCC, and it pretty much tells you what the types are that you care about. So that's kind of nice. If you have an auto variable, then you can use decltype to find out what the type for that is going to be. So if you want to know what auto is deducing, what you can do is you can say, okay, auto y is rx. I can then say TD of decltype of y. I want TD to be instantiated with whatever y's type is. So in this case, GCC will say, okay, TD of int has incomplete type, and that's what y's type is. It's an int. Microsoft says the same thing. Clang says essentially the same thing. So that's how you can deal with auto variables. Now, let us suppose what you would like to do is have a runtime version of what the types are. For some reason, you want the type to be produced at runtime. And the example I'm showing now is a little more realistic of the cases where you might begin to wonder what type the compiler is deducing. So in this case here, I've got some function template. It takes a reference to a const t. I've got some class widget. I have a function createVec, which is returning a vector of widget. And then I initialize an auto variable, which is const with the result of createVec. Then I say, well, OK, if it's not an empty vector, I call f with the address of vw sub 0. Now, we've got user-defined types in here. We've got containers in here. We've got auto in here. We've got templates in here. We're taking the address of things. It'd be easy to get a little bit confused as to exactly what the type is that we're dealing with here. And so you might wonder, OK, inside this template, what is the type of the parameter? And you might want to print it out at runtime. So here is a piece of advice. Do not use type info and call name. Because the answer you will get, in some cases, including this one, will be wrong. I say that with a certain degree of confidence because the standard requires that it be wrong. The standard actually requires that you get the wrong answer, which is kind of nice for someone somewhere. So in this case here, I say, all right, what I want to do is I want to print out type ID of t.name and type ID of param.name. So now, Microsoft's compiler, GCC, Clang, they all report the same results. What they say is that the type of the parameter is a pointer to a const widget. They say the type of the parameter is a pointer to a const widget, which is really weird because the parameter is a reference. I mean, it's a little bit strange that if I know the parameter for sure is a reference, it tells me the type is a pointer. That's just suspicious. It's because when you call type ID, which you have to do when you call type ID, it's because when you call type ID takes the expression that you pass it, and it is required to treat it as if it were being used to initialize a by-value parameter, which means you throw away the references and then you throw away any constant volatiles that happen to exist after that. It is required to give you the wrong answer. So if you were looking for a completely portable, 100% standards conformant way to get the wrong information, this is what you want. I do not know, short of writing it yourself, of a standards conformant way to get the right answer. Fortunately, other people have written it for you, and in the most recent version of Boost, they have a new library called Boost.type index. Boost.type index is generally a replacement, supposed to be a replacement essentially for type info. So it does a lot more than what I'm showing, but for our purposes, for my purposes, all I want to know is how can I print out a reasonable looking rendition of the accurate type that something has. So one of the functions they have is, actually I take it, one of the classes they have is type ID with CVR. CVR stands for const volatile reference. So type ID with CVR will give you information about the type of something without stripping off const volatile or reference. And then once you've got that, if you want to actually see it look nice in a human readable form, you can call the pretty name member function. So in this case, if I call that function with the same expression I showed you before and print out type ID with CVR of t.pretty_name and type ID with CVR of decltype of param.pretty_name, then GCC and Clang both print this out, and Microsoft's is slightly different textually but gives exactly the same information. I just didn't fit it on this slide. So if you're looking for runtime information, main thing is don't use type ID. Which leads me to decltype, because I've used decltype now, but I haven't actually talked about how decltype works. If you apply decltype to a name, then it will give you the declared type of that name. And it's not the same as auto, because auto, remember, if you auto will strip off references and top-level constant volatiles, and that's not what's going to happen with decltype. So if I have Rx, which is a reference to a const auto of x, then decltype of Rx will be a reference to a constant. It gives you the declared type, which makes sense. Decltype, declared type. So for things which have names, decltype does exactly what its name promises. If you have decltype of an expression that's more complicated than a name, then that expression is either an L value or an R value. If it is an L value, decltype will figure out what the type is, and then it'll slap an L value reference on it. So if you have an expression that is an L value, and you ask decltype for its type, you will always get back something which is an L value reference type. Usually, an L value reference expression already is a reference type. Almost always. So this is not going to change things most of the time. But there are some, so for example, in this case here, findVec is a function which returns a reference to a constant vector. Notice that findVec's return value is an L value because it's an L value reference, and it already has the L value reference there. So most L value reference expressions already have an L value reference. Excuse me, most L value expressions. It turns out that if you go into the C part of C++, C, of course, doesn't have any references, but it does have the notion of L values and R values. And so, for example, if I have a built-in array, and I index into that array, array sub 0, this is a built-in array. So array sub 0 is defined to be an L value, but it's not defined to be a reference. But it acts like a reference, because if you say array sub 0 gets 5, that will change array sub 0. It acts like it's a reference. It's just not defined that way. So L values always get an L value reference added to them. So if you say decltype of array sub 0, the result will be int ref. Decltype has a lot of little edge cases. I'm not going to talk about them. I'm just giving a little bit of information about decltype for purposes that I'm interested in. But the rules that I've shown you, decltype for a name, decltype for an L value, suffice for almost everybody almost all the time. If you're a hardcore library developer, you'll need to know more. Now, a name is an L value. So it's interesting to ask, well, all right, if a name is an L value, and I know that L values always get references added to them by decltype, what happens if I ask for decltype of a name? It turns out that the decltype name rule beats the decltype expression rule. So if you have decltype of a name, you get the declared type of that name. So if I say x is an int and I do decltype of x, the result of that will be int because x's type is int. But if I were to take x and turn it into an expression, for example, by putting parentheses around it. Now, parenthesis x parenthesis is not a name. It's an expression. So if I go from name to expression, then the expression rules kick in. So decltype of paren x close paren is actually int ref. So a name alone, you get its declared type. But a name as part of a larger expression, that can change things. And that has some interesting implications. I want to talk about function return type deduction, which is the last type of type deduction that we haven't talked about. So function return type deduction in C++11, there's not a lot of it. You only get function return type deduction in C++11 for lambdas that consist of exactly one statement. Everything else you had to say expressly what the return type is. But for C++14, the doors got thrown wide open, and now every function can have a deduced return type. All kinds of lambdas can have a deduced return type, which means that understanding how these return types are going to be deduced is more important than it has ever been. There are two possible return type specifications which lead to type deduction. One of them is auto. If you have a function using auto return type, the type deduction rules are those for templates. So this is important. Auto type deduction rules only apply for objects. If you have an auto return type from a function, you don't get auto type deduction, you get template type deduction. Just remember that's auto for template. And if you have a return type of decltype auto, I read decltype auto as the auto means I want to automatically deduce the return type, and decltype means I want to use the decltype rules. It's important to distinguish between them because sometimes auto is what you want, and sometimes decltype auto is what you want. So in this case here, what I have is a function, I called it lookup value. What this function is supposed to do is do a lookup and then return the value to be used. So in this case here, lookup value, I've got an internal data structure here, which I just call values. So I somehow compute which element of value should be returned, and then I say I want to return value sub IDX. In this case here, lookup value, I only want it to return the value. I don't want it to return a reference to that value. I don't want to let callers, for example, say, lookup value of my context info get 0. I don't want this to compile. I just want to return a value. So an auto return type here is exactly what I want, because an auto, remember, auto is never a reference type. So auto gives me the proper behavior here. But sometimes decltype auto is actually what you want. So in this case here, here's a function which I call authorize an index. So what I do is I pass in a vector and I pass in an index into that vector, and then what I'm going to do is authorize the user to make sure that they actually have permission to get this value, and then I'm going to return that vector indexed by that index. Now, v sub idx, that's going to return a reference to an int. And I want to let callers access that reference, which means I need decltype auto here. Pardon me? I'm sorry? OK, so the question essentially is, all right, couldn't I go back and put a reference here? And the answer is I could put a reference here. The answer is I could put a reference here. The problem is some vectors, their indexing operators, don't return references. And the poster child for this is vector of bool. They return proxy objects. And so if you want to write a function which will return whatever a particular expression returns, regardless of whether it's a reference or not, you need to use decltype auto. So in this particular case, because we know it's a vector of int, then we could just put a reference here. But if we templatized this for a vector of t, then we wouldn't know what it is again. Does that make sense? Okay. So in this case, we want to use decltype auto to get back exactly what this expression is. But decltype auto is very sensitive to the function implementation. In particular, let's suppose I write lookup value like this. So I get the return value from value sub idx, and then I say I want to return the return value. This is going to return an integer. If I put parentheses around it, it's going to return a reference to an integer. Now, notice what's happening here. I take my data structure, I copy a particular value into a local variable, and now I return the local variable as an int. That's OK. This is safe. However, if I take exactly the same implementation, I put parentheses around it, and there are some developers who routinely put parentheses around their return value expressions, this is going to return a reference to a local variable. This puts you on the fast track to undefined behavior. So when you are dealing with deduced return types, especially decltype auto, you need to be much more sensitive to exactly how you write your function implementations. As a general rule of thumb, if you're using function return type deduction, and if a reference type would never be correct, then what you want to do is use auto, because auto is never a reference. On the other hand, if a reference type might be correct, then you probably want to use decltype auto, assuming you don't know whether you want a reference or not. As a broader rule of thumb, I will say that I think that using deduced return types for functions in general is highly likely to lead to very confusing code, because it requires that readers of the code understand exactly what the type deduction rules are. And it also means that if you change the implementation of the function, you may actually change the return type inadvertently. So I encourage you to be cautious in your use of deduced return types for functions. They work great in C++11 for single statement lambdas, nice simple functions. You could usually see exactly what was going on. Now that we have deduced return types in general, which means you can write a very long function with multiple return statements and still have the type deduced, that seems a little iffier to me. So that's basically the story with type deduction. And this information is available in my book that I'm very pleased. This is the first time I've been able to show people the cover of the book, which also showed up on Friday. So anyway, I'm writing Effective Modern C++. So you can actually download the chapter on type deduction. Other places for more information, Thomas Becker has a website, C++ Auto and Decltype Explained, where he talks about these kinds of things. This notion of universal references and the special type deduction rules that they have, I wrote about that in Universal References in C++11. This paper 3922 that I referred to is this one here. One of the times when I expressed my frustration with certain situations was in this blog post. If braced initializers have no type, why is the committee so insistent on deducing one for them? I talked about the difference in type deduction rules for capturing by value versus capturing by init value. And that I wrote about that in Capture Quirk in C++14. I mentioned that I'm only talking about the type deduction rules as they relate to auto, because that was my initial motivation. If you are interested in all the details of exactly how type deduction works, at least in C++98, the book for that is still C++ Templates, that one there. And then the Boost type index library is Boost type index 4.0. That's the documentation for that is part of the Boost library. And we finished a little bit earlier than I had expected, but I'm hoping that there might be some questions. So any questions about anything to do with type deduction? Yeah, you'll have to speak very loudly. Okay, so the question essentially is, if you have a function with a deduced return type and you have inconsistent types being returned, in multiple return statements returning possibly different things, your program won't compile. The rule is that all the return statements must return the same type. If they don't return the same type, then your program won't compile. Even with the parentheses, it's got to be the same type everywhere. That's the rule. The alternative probably would have been to say we're going to use the same rules that are used for the question mark colon operator. If you have question mark colon, which has two different types, there is a deduced new type which is returned, which most people, including me, do not understand what the rules for that are. So frankly, I think it's reasonable that they said you have to return the same type everywhere. So, yeah. Okay, so the question is there any known reason for the capture quirk in the Lambda? What I like to say about the standardization committee is there is a reason for everything. So there is a reason. Now, so I suppose, let me go back and take a look at the Lambdas for a minute. This is my theory, because I just don't know. When you write a Lambda, in this case here, remember, this is generated by the compiler, so normally you don't see this as a human. All you see in the source code is this thing right here. So if you're looking at the source code and you say, OK, I'm going to capture CX and then use CX here, mentally you're thinking of this local variable. That's kind of the state that you're in. And so if this is const here, it would be easy to understand people thinking, oh, it's const. I don't have to worry about accidentally modifying it. So if you copied it in here and it stripped off the constness, in theory you might be surprised, because inside these curly braces, you're in the scope of the class, but you sort of think you're in the scope here. So my theory as to why they decided to retain const and volatile on Lambda captures was to avoid surprising people. That's my theory. When it came to a nit capture and a nit capture, here, this is a much more general thing, because you can have this be any arbitrary type of expression over here that you want to have. And so I think it was much easier for them to simply say, all right, we already have defined what type deduction rules exist, in particular for auto, so we're just going to reuse those rules. And so I think that they made two independent decisions which can be defended. I think the fact that both of them are in the same language at the same time make things a little more complicated. But that's my theory. Any other questions? Yes, yeah.
I actually don't have a question. I have two comments.
Okay.
The first one is we have microphones for people to ask questions. So if you have a question, please come up to the microphone and use it. That way your dulcet tones will show up on the recording. Not mine. Mine are not dulcet. And the other thing is a comment about David's and Nikolai's book. I know they're working on a new version for the updated language. As far as I know, they don't have any idea when it's going to be ready.
They're working on what again?
A new version of the templates book.
Oh, OK. Right, OK. All right, thank you. And your tones really were quite dulcet. Any other dulcet-toned questions? All right, then I guess everybody gets an extra long break. You can come up and talk to me afterwards. So, OK, so thank you very much.